One of the most useful applications of perturbation theory is to calculate the energy corrections for the hydrogen atom, particularly the corrections due to the fine structure and the Zeeman effect. Our present concern is actually for the energy correction to explain the fine structure of hydrogen atom, and after that we will discuss the Zeeman effect. In fact, when you talk about to the explanation of fine structure of hydrogen spectrum, this in turn is due to two effects. First one is a spin orbit coupling and another is relativistic correction. In the present lecture, we are going to see how we can calculate the energy correction due to the spin orbit coupling. Okay, only our discussion will be limited to calculation of energy correction due to a spin orbit coupling. And in the forthcoming lecture just after this, we will see the relativistic correction and explanation of fine structure of hydrogen spectrum. Okay. Again, first of all, when you talk about the spin orbit coupling and how much energy is due to this spin orbit interaction developed in the hydrogen atom, first of all, we will calculate it by the classical concept. But after getting the result for the spin orbit energy using classical idea, we will convert that result into the equivalent quantum mechanical result for the spin orbit energy. Okay. So first of all, we are going to see how we can calculate the spin orbit energy or spin orbit interaction energy, you can say, by the classical approach. Okay. So when this question will be asked in your examination, to make the length of the answer short, you may use the final result of the classical approach and you can mention it directly for writing the answer. Okay, but as our aim here is to discuss the thing in very detail, so I am not writing the expression for a spin orbit energy directly, but we will calculate it but by classical approach. Okay. In fact, the spin orbit coupling in hydrogen arises from the interaction between the electron's spin magnetic moment mu_s, which is given by this formula, and the magnetic field produced by the proton or the nucleus of the hydrogen atom. But one can think that proton is stationary, and classically a stationary charge does not create magnetic field. When the charge is in motion, then it creates magnetic field. So definitely when you will take the proton or the nucleus in a rest frame, then it cannot produce magnetic field. But if you consider a frame relative to which the proton is in motion, then you can say that proton can create magnetic field. Actually, situation is here will be like that. In my course provided to you on atomic and molecular physics, actually I have discussed that the electron possesses magnetic moment. It behaves like a tiny magnet, and its magnetic moment mu_s is given by this formula. This is minus Es times Me times C. Here this minus E is the charge of electron, this capital S is spin angular momentum of the electron, and you know the magnitude of this spin angular momentum is given by a small s times s plus 1 square root times h bar. Here actually this s is equal to 1 over 2. This is the spin quantum number, and so the magnitude of this vector s is equal to 1 over 2 times 1 over 2 plus 1 square root times h bar. And so actually this is root 3 over 2 h bar. Okay, and me is mass of electron, c is speed of light in free space. As you know that in classical approach or semi classical theory provided by Bohr, we consider that in case of hydrogen atom, the proton is situated at the nucleus at rest, and electron is moving with a velocity v in a circular orbit. So if you consider the proton as a rest frame, then with respect to this stationary frame, the electron is in motion with velocity v. Okay. But now if you consider that we consider that our frame is attached with the electron, so in its own frame, reference frame, the electron will be stationary. Okay, and in that condition, when an observer will observe the proton or the nucleus with respect to the rest frame of the electron, as I have shown in this figure, then such an observer will find that the proton is moving with velocity minus v, okay, in a circular orbit of radius r. So in this condition, you can say that in the rest frame of electron, proton is in motion, and that proton will produce magnetic field. You know, classically the production of magnetic field is frame dependent. Okay, a charge which is stationary in a frame that may be in motion in another frame. So in first frame in which the charge is at rest, we simply say that such a charge cannot produce magnetic field, but in a frame relative to which our charge is in motion, you simply say that in that very frame that charge will produce magnetic field. So here in the rest frame of the electron, the proton is in motion, and so this proton will create a magnetic field, and in that magnetic field this electron is situated. Okay, this electron will be situated. So in fact the origin of the magnetic field experienced by the electron moving at velocity v in a circular orbit around the proton can be explained classically in as I have told you that the electron within its rest frame sees the proton moving with velocity minus v in a circular orbit around it, as you can see in this figure. And you know, from classical electrodynamics, I have provided so many videos, almost more than 50 videos on classical electrodynamics. You can go through the playlist of EMT and classical electrodynamics of my channel, and there you will find such a concept. So in accordance with classical electrodynamics, the magnetic field experienced by the electron in this condition is given as this. If B is the magnetic field which is produced by the proton, and this in this field there is electron, and that electron actually experiences this magnetic field which is given by minus V cross E over C. V cross E over C. Now if you will multiply Actually, our aim is to express this expression in terms of momentum of the electron. And for this, let us multiply this expression by ME in numerator and also in denominator. So the result remains same. But ME times V, this is written as P, which is the linear momentum of electron. Okay? And divided by MEC across E. Here E is the electric field. But how this electric field is present here, we will just explain it from where this electric field comes in this expression. Okay? So B is given as E cross P divided by MEC. The vector product of two vectors is not commutative. A cross B is equal to minus B cross A. So minus P cross E can be written as E cross B. And that's why we have written that this B is equal to E cross P over MEC. Okay, over MEC. Actually, here, as I have told you, that P is the linear momentum of the electron and E is the electric field produced by the proton's Coulomb field. And the charge of a proton is plus E. Okay, because in hydrogen's nucleus there is only one proton, so I am not talking about nucleus, simply I am saying a proton. Although in figure I have written here plus ZE. It means if the atom is not hydrogen but hydrogen-like atom, then there may be more than one proton. For example, if you are talking about the He plus ion, okay, or Li double plus ion, these are actually hydrogen-like atoms. Okay, although these are ions, but these are called hydrogen-like atoms because He plus, Li double plus both has only one electron, okay, moving in the closed shell, and therefore these are called hydrogen-like atom. So this theory is also applicable for hydrogen-like atom. And if at a distance r, you have to find the electric field produced by this plus E charge of the proton. This is just a point charge. And from electrostatics in CGS unit, this field is given by E over R square times R hat, where R hat is the unit vector or radial unit vector in the direction of the electric field. And this unit vector R hat may be defined as vector R over modulus of R. And that's why this ER can be given by E times vector R divided by R cube. Okay. So this is the Coulombian field which is produced by the proton at the site of the electron. I have written this expression in CGS unit because we will follow the CGS unit. If your aim is to write down this expression in terms of SI unit, only you have to multiply this result by a constant factor 1 over 4 pi epsilon naught. Okay. So this is a constant factor, so it is easier to deal the problem in making the calculation in CGS unit because we have not to write this factor time to time. Okay. Now, if you are talking about the more general problem of hydrogen-like atoms, as I have told you, that is the hydrogen atom means atoms with one valence electron outside a closed shell, where an electron moves in the central Coulomb potential of a nucleus. Okay? Then the potential energy, this V of R is what? This is the potential energy of this system. And if the potential at this site is phi of R, okay, where electron is located, and this potential is produced by this proton, then charge of electron times potential is equal to the potential energy. So this V of R represents the potential energy, although quantum physicists uses the term potential instead of potential energy. But here phi of R, you can say this is the scalar potential, and V of R, this is potential function or potential energy function. Okay, and you know that this electric field is related to the scalar potential phi of R by this relation. You know, electric field is given as negative of the gradient of electrostatic potential, and so E of R is given by minus gradient of phi of R. But see here, if you will obtain the value of phi of R, that is this scalar potential, this will be equal to minus V of R divided by E. Okay, so instead of phi of R, you can write minus V of R by E. So this minus times minus will become plus, and your result is E of R equal to 1 over E gradient of V of R. Here this V of R, as I have told you, this is potential energy. So in present situation, since you are considering that the potential is the central Coulomb potential, and you know in case of central potential, this V is only a function of R, not of theta, not of phi. So instead of this gradient operator, you can use d/dr operator. Okay, because the potential is central. So this V is not a function of theta and phi, and that's why you can write this E of R equal to 1 over E, and when you will put the value of this V of R, sorry, this value of this will be in fact R divided by R. This is the unit vector for this in the direction of E, and dV/dr. So the electric field produced at the site of the electron by the proton, treating the potential created by the proton as just Coulombian potential, you can express the electric field in this manner. Okay. So the magnetic field of the nucleus calculated in the rest frame of the electron is obtained by inserting equation 2 in 1. Okay. So in this way you have calculated the value of E of R, and you can see in the expression for the magnetic field which I have mentioned in equation 1, now you can use that expression for E to get the magnetic field. In the rest frame of the electron, this field is produced by the proton, because in the rest frame of the electron you see that the proton is moving. Okay, and that's why B will be now given by 1 over M.Sc times E cross P. Okay, E cross P, and E cross P, E is equal to this much. So let us put the value of E from there, and then it will be 1 over E times M.Sc times 1 over R cross P. Okay, but you know, according to classical mechanics, this R cross P is what? This is the orbital angular momentum. This is orbital angular momentum. Okay, and this orbital angular momentum is denoted by the symbol this. Okay, sorry, here there will be dV by dr, dV by dr, 1 over E times M.E times C times 1 over R dV by dr, R cross P. Okay, and r cross p is replaced by L, which is orbital angular momentum of the electron. You can see I have mentioned it here. So in this way, you have obtained the classical formula or classical result for the magnetic field produced by the proton in the rest frame of the electron. Okay. Now you know the negative of the scalar product of a spin magnetic moment and the magnetic field gives the energy of interaction. Our electron here behaves like just a tiny dipole, and this dipole is in an external magnetic field B. So there will be a magnetic interaction between the dipole and the magnetic field, and due to this interaction energy is developed in our system. And this interaction energy I have written by the symbol H hat SO. In fact, here H hat, this is just Hamiltonian. Interaction energy means Hamiltonian. S subscript stands for spin and O for orbit. So I have written the subscript SO for the sake of simplicity, that it will refer a spin orbit interaction. We will talk about it later on, but here symbol has been already used. Okay. But you know, mu s is given by what? This is given by minus Es divided by MEC. So instead of mu s, now you can write E over MEC times vector S, where S is the spin angular momentum vector. So HSO, this is E over MEC times S dot B. Okay, minus minus here become plus. But the value of B we have already calculated here in this equation 3, considering the rest frame of electron. Okay. So when you will substitute now the value of B obtained in this equation 3, then this HSO is given as 1 over ME square C square times 1 over R dV by dr times S dot L. Okay, times S dot L. So in this way we have obtained the value of the interaction energy of this system due to the interaction with the magnetic field. Okay. Actually, this energy which we have calculated here in this equation number 4, actually this energy turns out to be twice of the observed spin orbit interaction. When the actual in experiment the energy of interaction due to a spin orbit interaction is obtained, it is found that the actual value is just half of this value. It means this result is just twice of the actual or the observed value of energy of interaction due to a spin orbit interaction. Okay. Why this energy which we have obtained is just twice of the spin orbit interaction? The reason behind this is that this equation, that is equation 4, or this value of HSO, has been calculated within the rest frame of the electron. I have used this term rest frame of electron several times. Okay. But this frame is not inertial, because you know, actually according to Bohr's model, the electron moves in a circular orbit, and in circular orbit if the electron is moving, then definitely it will have centripetal acceleration, or you can say that its motion is accelerated motion while moving in this circular orbit around the nucleus. And therefore the treatment of electrons frame as a rest frame is not appropriate. Okay. In fact, for a correct treatment, we must transform the rest frame of the nucleus, that is the lab frame. Okay? And this transformation, which involves a relativistic transformation of velocities, gives rise to an additional motion resulting from the precession of this mu s. Okay, and this precession of mu s is called Thomas precession. What is this? This precession is called Thomas precession. Thomas precession. Just you have studied in your course on atomic physics the Lamar precession, that is the precession of angular momentum vector. Here this precession of mu s is called Thomas precession. Okay, and actually the precession of the electron spin moment is a relativistic effect, and it occurs even in the absence of external magnetic field. Okay, so the transformation back to the rest frame of the nucleus leads to a reduction of interaction energy defined in this equation 4 by a factor of 2. This is the cause. Although I have not written all these facts, so I understand you have clearly now an idea why this value of energy which we have obtained by classical concept deviates from the actual observed value when we consider the spin-orbit interaction. Actually, the actual observed value is just half of this value. And why just half? The reason is actually the Thomas precession. Okay. So I have mentioned here that the observed interaction energy is just half of this value, and this is due to the fact that this equation 4 has been calculated within the rest frame of the electron, and this frame is not inertial as electron is in accelerating circular orbit. So for the correct treatment we transform to the rest frame of nucleus and obtain that the actual value of HSO is just half 1 over 2 me square c square times 1 over r dv by dr s dot l. Okay. Now as you can see that this result has been derived from the classical treatment. The result which you have derived in this equation 5, this result has been derived completely using the classical idea or the classical treatment. But you know that a classical result, a quantum mechanical result from a classical result can be obtained simply writing all the observables in the expression in operator form. So when you will write the corresponding operators for all the observables in equation 5, this equation will be the quantum mechanical version of the expression for this interaction energy HSO. So you can say that we can obtain the corresponding quantum mechanical expression by replacing the dynamical variables or observables with the corresponding operators. So now you can write that this interaction energy HSO, this is equal to 1 over 2 me square c square over times 1 over r and dv hat by dr. Now mark the difference. In the classical result we write dv by dr, but now in quantum mechanical result we simply write v hat instead of v. This v hat is the operator corresponding to v. Okay, and similarly instead of s we write s hat, instead of l we write l hat, which are actually the corresponding operators for s and l. Okay. So in this way, first of all, we have obtained the interaction energy simply by classical treatment. And after getting the result, using the fact that any quantum mechanical expression can be written in any classical result can be written in quantum mechanical version by replacing the dynamical variables or the observables in the expression with the corresponding operators. Okay. So in fact, this equation 6 now defines the spin orbit energy. Okay, spin orbit energy. And now we will particularly apply this result for hydrogen atom, because our aim is to explain the fine structure of hydrogen spectrum. So now, if you are talking about the electron of hydrogen atom, then what is the value of this V of R? V of R, this is the potential energy, and in the nucleus of hydrogen atom there is a proton having charge plus E. Here there is electron whose charge is minus E, and both are separated by R. So the electrostatic potential energy of this system is simply minus, since interaction will be attractive, minus E times E divided by R, that is minus E square by R. And if you will write this expression in SI unit, there will be 1 over 4 pi epsilon naught E square by R with negative sign. This negative sign actually shows that the interaction between proton and electron will be attractive. Okay. So V of R in context of hydrogen's electron is this much. Now in our expression there is dV by dr. So let us find the value of dV by dr, and you can see this dV by dr will be equal to E square by R square. You have to differentiate 1 by R, and that will be minus 1 by R square. So use this value of dV by dr in this equation 6, and then you will get the HSO, that is the spin orbit interaction energy, particularly for hydrogen atom. Okay. So replacing dV by dr by E square by R, our expression for HSO is E square over 2me square C square times 1 over R cube times S dot L. Okay. This is the final result, result for our calculation of spin orbit coupling or spin orbit energy. Okay. In the beginning of my lecture, I have told you that when this question will be asked in your examination as an application of perturbation theory, then it is possible that you remember this result and write this result directly for the further calculation. You may escape all the previous calculation if you are able to remember it. It is only for writing answer in your university examination, not for knowledge. For knowledge you have to understand each and everything. Okay. Till now we have only calculated the interaction energy due to the spin orbit interaction, but this interaction energy is due to the spin orbit interaction. If we will neglect the spin of the electron in case of hydrogen atom, this energy will vanish. Okay. So this is the perturbation. This is the perturbation. Due to a spin orbit interaction, an additional term in Hamiltonian will get added. So when now we are going to talk about the perturbation theory applied to explain the fine structure of the hydrogen spectrum, then we have to find the energy correction, particularly to first order. Okay, in case of hydrogen atom, uh, and what will be the perturbation term? Actually, this HSO will be the perturbation term. Okay, and so in the unperturbed Hamiltonian, when you will add this HSO, then you will get the perturbed Hamiltonian H. And finding the energy eigenvalue and the eigenfunction for that Hamiltonian, you can get the value for the energy correction. Okay, and that energy correction will lead to the fine structure of hydrogen spectrum. So now let us proceed to apply perturbation theory to calculate the contribution of the spin orbit interaction in a hydrogen atom. Okay, as I have just told you that due to a spin orbit interaction, the perturbation is HSO, and this is this much you have already obtained, and therefore the Hamiltonian now will be given by H equal to H naught plus HSO. You know this H0 or H naught. What is this? This is the unperturbed Hamiltonian. This is the Hamiltonian for which the Schrodinger equation can be solved exactly. And this is the perturbing Hamiltonian or perturbation term. And you know, the unperturbed Hamiltonian H hat is equal to what? This is P hat square over 2me minus E square over R. Actually, this first term is the kinetic energy operator, and this is the second is the potential energy operator. Okay, and HSO, this is defined here, and so substitute the value of HSO. So this is your Hamiltonian in present case after considering the perturbation term. Okay. Now, if your aim is to apply the perturbation theory, first of all, we need to specify the unperturbed states. When you say the unperturbed states, what does it mean? It means you are talking about the eigenstates of the operator H naught hat. Okay. Now you have studied earlier in your course on quantum mechanics that the spin of the hydrogen electron is taken here into account. So definitely the total wave function of this H naught consists of a direct product of two parts. The first part is the spatial part that depends only on space coordinates, and another is the spin part, spatial part and spin part. Actually, to specify the eigenstates of unperturbed Hamiltonian H naught, we have two choices. In first choice, the joint eigenstates is written like this. This is N L M L MS. Okay. This is the first choice. These are the eigenstates of vector L hat square, okay, S hat square, LZ, okay, and SZ. Okay, and in the second choice, actually the eigenstates are denoted by this. Sorry, here there will be in this form. These are N, L, J, M. Okay. If you are talking about the H naught, it means the unperturbed Hamiltonian. then the while H naught is diagonal in both of these representations. So HSO is diagonal in the second but not in the first, because HSO, or you can say more precisely S dot L, commutes with neither LZ nor SZ. If you have not an idea of this commutation, you can watch my previous video in the chapter angular momentum. There you will find it. Okay. So actually in this condition, if HSO were included in the first choice, then actually this first choice will be your bad option, because we would be forced to diagonalize the matrix of HSO within the states. Okay. And this exercise is nothing less than tedious and cumbersome. Okay. So the second choice which I have mentioned here, this is actually the very simple and very ideal for dealing our problem. Okay. Since the first order energy correction is given simply by the expectation value of the perturbation of this HSO, okay, and therefore you can write the eigen states and the eigen values for this state. Okay. Now the eigen states of this S dot L, you can see eigen states of this S dot L. Actually this has been discussed in the chapter on angular momentum. So you have to remember it, because we have discussed it previously and here there is a need, so you must remember it. So the eigenstates of S dot L are given by this expression psi n comma L comma j equal to L plus minus half comma m, and this is equal to R NL of R times a square root of L minus plus m plus half divided by 12 plus 1 y L comma m plus half. Okay, this is radial wave function, and this y is the spherical harmonics operated on this ket 1 by 2 comma minus 1 by 2. Okay, and plus minus a square root of L plus minus m plus half 12 plus 1, and y L comma m minus half ket 1 by 2 comma 1 by 2. Okay, and as I have told you, you must remember it, because I have not derived it here, because it is the subject matter of angular momentum chapter and you can find it there. Okay, but you know, the total angular momentum vector J is the vector sum of the orbital angular momentum L and the spin angular momentum S. Therefore, if you will take that a scalar product of this equation with itself, what will be the result? Then J dot J will be L plus S dot L plus S. But you know, J dot J, this will be J square, and this will be L dot L plus S dot L plus S dot L plus L dot S. Okay, and L dot L, that will be L square, S dot S is S square, and S dot L plus L dot S, both are same, and this will be 2L dot S. Okay, so L dot S is equal to 1 over 2 this much. Okay, now you can find the eigen values of this L dot S. This equation 9 defines the eigen vector or eigen state or eigen function for L dot S. Now we are going to find the eigen values or the eigenvalues corresponding to this eigenfunctions we are now going to find. Okay, and L, the expression for L dot S is this much. Eigenvalues are what? Actually, when you say that we are going to find the eigenvalues of L dot S, it means you are going to find the expectation value of L dot S with respect to this state. Okay, get NLJ. And what will be this? The eigenvalue of the operator J is root over J into J plus 1 times H bar. The eigenvalue of L is root over small l into L plus 1 times H bar. And the eigenvalue of S is root over, small s into S plus 1 into H bar. But just in the beginning I have told you that this S is fixed, this is 1 by 2 for electron, and therefore this is root 3 by 2 H bar. Okay. So see this expression for L dot S and substitute the values of J square, L square and S square from here. After substituting this, you will get the eigenvalues of this L dot S, and these are this will be H bar square over 2 times J plus 1 minus L times L plus 1 minus 3 by 4. Okay. So these are the eigenvalues of L dot S. Okay. Now after getting the eigenvalues of S dot L or L dot S, you can now find the eigenvalues for the Hamiltonian H, which I have defined in this equation 8. What will be the eigenvalues of this Hamiltonian H? Since this is H naught plus HSO, so the eigenvalues of H will be eigenvalue of H naught plus eigenvalue of HS naught. Okay, and this is the eigenvalue of L dot S. Okay, this is the eigenvalue of L dot S. So the eigenvalue of H will be eigenvalue of H naught, and the eigenvalue of H naught, this is equal to En0. When you say En0, this is actually the energy levels of hydrogen atom. Okay, and plus the eigenvalue of HSO, and eigenvalue of HSO is given by this expression. This is expectation value of HSO. Okay. So ENLJ, these are the eigenvalues of Hamiltonian H defined in that equation to first order correction. Okay. But for hydrogen atom, the energy of this atom in for nth quantum state, this is given as minus E square over 2a times 1 over n square. So in CGS unit, so instead of this En of 0, I have written this much. Okay, and the expectation value of HSO corresponding to these states is denoted by the symbol ESO1. Okay, where ESO1, this is energy due to spin orbit interaction. Okay, but what will be ESO1? This is nothing, this is simply the expectation value of HSO. Okay, and you can see the expectation value of HSO will be given by how we can find actually the expectation value of this. Actually, this is given as see here. HS, value of HSO, you can see we have calculated the value. Yes, this is the value of HSO. But here you have to take the expectation value of 1 over r cube times this much. Okay, E square by 2 me square c square is a constant factor, so this will be outside, and you have to take the expectation value of 1 over r cube times expectation value of S dot L. Okay, so let us see. When you will use that result, the constant factor will be E square H square over 4 me square c square. Okay, and the expectation value of S dot L, that is this much times some constant factor which is already included here, and the expectation value of 1 by r cube, this is written like this, NL with respect to the quantum state NL, this is the expectation value of 1 over r cube. Now again, the expectation value of this 1 over r cube with respect to the state NL is calculated, which you have learned in my previous videos. So here I am writing this result directly. This is the expectation value of 1 over r cube, which is given by this expression. So you have to remember it here for writing your answer in your examination. So this is 2 over n cube times L plus 1 times 2L plus 1 times A naught cube. Here, n, you know, this is the principal quantum number, L is the azimuthal quantum number, and what is this A naught? A naught is the Bohr radius. It is Bohr radius, okay, which is equal to 0.529 angstrom. Okay, so let us substitute the value of this expectation value of 1 over r cube here, and then you will get the value of ESO1. So after substituting that, you will get the expression for ESO1 is E square times H bar square over 2me square c square times this much. Okay. Now we will write this expression for ESO in a suitable form, and for this we actually arrange the terms like this. You can see this expression can be written as E square over 2a naught times 1 over n square times H bar over MECA naught whole square. Actually, you know, the energy En 0, this is given by minus E square divided by 2a naught times 1 over n. But here there is not minus sign. Okay. So instead of this, we can write modulus of En0. And for H bar over MECA naught, we write alpha. So this is alpha square and divided by this n and the remaining factor. So this is actually the energy of interaction ESO1 in terms of En0 and alpha. Actually here this alpha is a very important parameter of spectroscopy. This is actually a number, this is a dimensionless parameter or constant which is known as fine structure constant. You can see I have written this alpha instead of H bar over MECA naught. But you know, this Bohr radius A naught is given by H bar square divided by ME into E square. Okay. So when you will put the expression for A naught here, this will be H bar over MEC times ME into E square over H bar square. Here this Me and Me will cancel out. One of the H will also cancel out. So the expression for alpha is E square over H bar C. Okay. And all quantities here are universal constant, you know. So when you will put the numerical values of E, H bar and C, it is almost equal to 1 over 137. 1 over 137. So remember this value of fine structure constant alpha. So in this condition, you can express this En0 in terms of alpha. As you know, En0 is given by this expression, and so using the expression for alpha, which is E square over H bar C, you can write or using this expression H bar over MECA naught, you can write this expression for En0 minus alpha square MECA square over 2n. Okay. So instead of this modulus of En0, now you can write alpha square MECA square over 2n. Okay. So you can express the expression for ES01 in terms of the fine structure constant, and this expression will be like this: alpha to the power 4 MECA square over 2n cube times this much. So in this way we have calculated the spin orbit energy correction term to the first order. As I have told you that in this lecture we will see only the energy calculation due to this spin orbit interaction in case of hydrogen atom. But in our forthcoming lecture, the whole concept will be completed. So in forthcoming lecture, you will see the second part of this concept. And in that concept, we will discuss relativistic correction and then the explanation of fine structure of hydrogen spectrum. Okay. So I think you have clearly understand the calculations which I have made, and definitely you have understand the concept which I have discussed. Okay. Thank you very much.